So from now till a while, till we end operation transformation, we are basically going to discuss consistency in various forms. Okay, and we looked at consistency problems that can occur when people have concurrent operations, and we'll assume in this discussion that messages get reliably to the other party. Okay, but what we're going to concern ourselves is order. Okay, and order issues become order is an issue when you don't have relayed communication, when you have direct communication. Okay, so we're going to look at this situation where you have multiple parties communicating with each other directly. Messages reach reliably between two parties. Okay, and we want to have some kind of global ordering that's consistent on all the computers. So this is a situation we are multicasting. Okay, and a user process is using our communicator to send messages to everybody else. We're going to assume pretty much multicast is whenever you send a message to more than one party. Okay, but pretty much in our discussion we're going to assume two others. Okay, and the question is same message directed to multiple processes, and receiver of multicast message can also multicast in general. And the question is, are there some consistency issues here? And if so, how can we address them? Okay, and there's many ways to present this. The way I understood this was to say, okay, let's take n equal to 2 first, see if I can understand it. And we'll go from n equal to 2 to n arbitrary. Okay, so an n equal to 2 case is actually not unfamiliar to you guys. How many of you have done networking, TCP/IP? Okay, so from that knowledge, you should be able to consider the n equal to 2 case, which means that the TCP/IP ordering stuff, it's not going to be exact TCP/IP, just translates very directly to causality, which is what we're going to discuss next. Okay, so there's a relationship there which I'm going to show. Okay, so let's consider n equal to 2. And now TCP/IP tries to do two things at the same time. It tries to go and provide messages in order, and it also tries to provide reliability. They are two coupled together. It's a nice efficient algorithm that does both. Okay, we're going to do something inefficient. We're going to assume there is some way to do reliability. And the next question is, how do we do ordering? Okay, so this is not the algorithm TCP/IP uses, but this algorithm that I'll show you will generalize to the n case easily. Okay, so assumed reliable delivery, and how do we do in-order processing? And like I said, it's not practical to decouple, but will help us draw out the principles for the n-computer multicast case where reliability is assumed. Okay. So what can go wrong when messages are being delivered in order, in reliably, but not in order? Okay, and this is not entirely fake example. Let's say this is around lunchtime. I send a message to you saying, hey, are you done? And then I say, lunch. Okay, and this is exactly what happened the first time I used IM with a colleague at Microsoft. And the messages get out of order. Okay, so this person gets a lunch first and done next. And he's saying yes to lunch, but I'm not done. Right? That's what he's saying. What I hear is yes to done, but no to lunch. Okay, so I don't get to go to lunch. It's a little more complicated scenario. I actually, when that happened, I captured the screenshot. It's still around with me to show what can happen when you don't have causality in IM. Okay, and that had to do with the fact that we both entered messages concurrently. Okay, so that was more complicated. So so we have divergent state, and how do we solve this problem? How do we ensure reliability in the two user case?
Make sure same order.
How do we ensure order at the receiving end? The fact is that messages came, one message went through China, the other went through India, and who knows which,
So,
Sorry?
yeah,
Acknowledgement is for reliability.
sequence number.
Sequence number.
Yeah.
Okay? You say, this is my message number 5, and this is my message number 6. And that number is sent with to the other side, and the other side then has to keep count of how many messages it has received from you, and if a message is so what do we do if a message is received out of order?
In order work.
What will we do with the message?
Reorder.
How do we I mean, the message has arrived, it's out of order.
Yeah.
What does Steve buffer it? Okay, so that's the basic idea in this causality thing. You somehow figure out what the right order is. If it's not the right order, buffer it. Things are reliable, so the preceding messages will arrive at some point, and then you go and play them in the right order. Okay, in the demo I showed you, that's exactly what happened that we do tonight. Okay, so we'll carry on from here next time. I do want to talk to you guys about how this whole experience could change. And Patrick mentioned we could have people watching the videos offline and maybe have answering questions in class. So rack your brains about that, because we've got a brave new world now to explore. And you guys, looking at all the media that you have available, you're in a very good position to figure out what could be useful here. Okay, so let's go back to causality. And actually, we were not looking at causality. We were looking at a simpler idea, which involved two sites. And we said that the messages go between those sites reliably. Somehow that's happening. Okay? And given reliable communication, how can we make it in order? Okay, now that's not a practical problem, because both these problems can be solved in one algorithm. Okay, but when we go to multiple sites, we can assume that between two sites, messages are both in order and reliable, and we have to create a global order. Okay, so the algorithm will come up for two sites will just translate nicely to multiple sites. Okay, so the example I gave you was that once to motivate this, that one site goes and generates a message that is intended to arrive at another computer but doesn't arrive immediately. That site generates another message which arrives earlier. So we have these two messages in the wrong order. Okay, and we have divergent state. Okay, so what we see here is that the messages went out of order, and the state here diverged. So what did we talk about as a solution to this problem? So we timestamp messages. So this has a timestamp of 0 or 1, and this has a timestamp of 2. And to generate timestamps, I need what at this site? I need a variable, a clock. Okay, and yeah, we could just go. So timestamp, yeah, we could just go and put the real time. Okay, and if we put the real time, what happens when this message arrives here? Oh, sorry. When this message arrives here, what should the site do with the time? It says, okay, it was sent on Monday at 10 o'clock. Compare with local times. So local time is greater than 10 o'clock. So I was hinting, so that doesn't seem to work, right? This site doesn't really know that this message is out of order. And from your knowledge of TCP/IP, what should we do instead? So have a logical timestamp. Okay, which is, so logical versus physical. Physical means the actual time. Logical means it's relative to a particular process. And it has to do with the message order rather than with the time, okay, which is physical time. So we have a counter, and that counter is 0 initially. And what happens? We have a variable here, and how does the variable change? When does the variable change? Whenever you send a message, you increment the variable, and then what do you do with the variable? So just as Patrick said, timestamp the message, we logically timestamp the message. And what should this site do when it sees that message number 1 arrived from PC1 or message number 2?
It knows that a message that is sent before that message is still on the way, so it waits.
How does it know that message number 1 has not arrived? It hasn't received it.
Yeah.
And had it received it, what would it have done? It would have kept another variable that says how many messages have I received from this site. So each site keeps an account of number of messages it has sent to the other site, and also keeps account of how many messages it has received from that site. It says, how many messages, or what? Or is there a better variable thing to keep?
Latest number.
Latest sequence number. Okay, that's what TCP/IP pretty much does. Okay, so we have two variables, local counter and remote counter. Okay, and now when this message arrives out of order, what should it do?
Compare the sequence number in the message and its local copy of the counter.
Okay, it compares the number in the message and its copy here, and then if it finds that it's out of order, then what should it do?
Delay processing that message.
Delay processing the message, which means you're saying something, cache it, okay? Put it in some buffer, okay? And now, when this message arrives, what should it do? Display them both, right? And it should really display them both. It knows that this message is fine because it's the next message. And then it should go and look at the buffer to see if some message is eligible for delivery now. If so, all the messages that are eligible for delivery, deliver them. And then what happens to the counter here for the remote site? What value should it have at the end of processing both messages? So when it processed this message, the count went to increased to the count that was enclosed, basically. Or you can say increased by 1, or you can say it became the count here, right?
Yeah.
And then when it processed the buffered message,
Increase again.
same thing. Every time it processes a message, it says, what's your count? Let that become my count. If the message is sitting in the buffer, it says, I'm not going to look at your count. I mean, I've looked at your count, but I'm not going to use your count to update my count. Okay? Each computer pair keeps count of number of messages sent to the other party. Okay? So that's a local count. When this guy generates a message done, it increments the local count and attaches that as timestamp, as a logical timestamp. So it is incremented local to 1. Attach that number to done. And then it generates another message. It increments the count again, sends the message with 2. Okay? Each computer keeps processed remote number and ordered buffer for other party. Okay? So it knows that, the last, has received no message so far from the other site. And so it's got this remote counter. Both sites have got that. It's got a buffer also for that site. When message received, put message in ordered buffer. Just as an algorithm, we just put it there. Okay. Now you go and process the buffer. If buffer empty or message number is not equal to successor of remote number, so we know what the next number expected is. The message number 2 is not the successor of that. So we just return and say, okay, it stays in the buffer. Now this message arrives. What do? We put it in the ordered buffer. It's an ordered buffer, so you have to insert it at the right position. We insert it right here. Okay? And what's the next step now? If buffer empty or message number is not equal to successor, return. Okay? That's not true. So we go to the next step, remove message from buffer and process it. So we go and remove the message. Process the message, remove it. And what should we do now at this point? Remote number equals message number. You can say increment, or we can just make it that. Okay? And next step after this, check it again. Okay? Remove message. Remote number equals this message number. It becomes 2. Okay? So that works nicely. And that's the basic point now. After this, that's the basic algorithm. Now we got to make it work for end users, which will be a little tricky. But let's just, when I go to end users, I can go to end users in 2 different ways. I can say there are n unicasts around. Okay, so there are 3 sites. Each site is unicasting to every other site. Okay, so it's got a local, so PC1 has a local for 2 and remote for 2, local for 3 and remote for 3. Okay, so it has these independent pairs, independent pairs, independent pairs. Okay, so each connection has got this remote and local on that connection. Okay, so when you create a process and have 5 socket connections to 5 different sites, that's essentially what's happening. Okay, but we want to go beyond that, and we want to support group IO. Okay, where we know that this site is communicating with multiple sites, and there's some kind of global order we want. Okay, we know how to get order between 2 sites. Now we want order among multiple sites. Okay, and go and see an example. So I say done, and I send this message to not 1 site but 2 sites. Okay, this site has got the message. The other site has not got the message so far. And what bad things can happen now? I'm trying to ask 2 of my friends, are you guys done? Okay, we know how to get messages between 2 sites in order. Can we come up with something bad, given that there are multiple sites? So this message has arrived at site 2. It hasn't arrived at site 3. Because it's going to take a long time to go to site 3.
So then site 2 sends the response to both sites, but then site 3 has no context.
Okay, so site 2 gets done, says, oh, yeah, I'm done, and how about lunch, guys? That lunch arrives at this other site, right? It has no context, or it has the wrong context, right? Arrives here, and then this message arrives here, right? And what does he say? He says, done, and says, yes, no. Yes, I'm ready for lunch. No, I'm not done. Okay? And we have divergent state. Okay, and this yes, no means different based on this context rather than here. Okay? So this person is ready to go for lunch, and they all think this person is not ready to go for lunch. Okay, so they go between the 2 of them. Okay? So how can we go and solve this problem now? You can solve it for 2. Can you solve it for n? Trivially? Non-trivially?
Have a shared model that had sequence numbers or something like that for everybody, or for the whole conversation.
Okay, so let me quickly go in before I ask Nick. Okay, firstly, what do we want really? Before we say how to solve the problem and how can we have a global sequence number, what's the correct order here? Okay, these 2 are the correct. Which of this is correct? This or this? Why? So you're saying this guy, PC2, send the message lunch after done. That's why. Or to put it another way, this message was caused by this message. That's a causal relationship. And this causal relationship is being honored here, but not being honored here. Okay? That's another way to put it. Okay? That's why the word causality comes in. Okay? So M1 causes, so we want a way of ordering messages. We want some value to order messages. And here's the criteria for ordering messages. That M1 causes, M1 is less than M2, or M1 causes M2 if M2 sent from site S after M1 received, okay, or generated a site S. Does that make sense? Why is, so if there's only one site sending two messages to another site, then the causal order is basically that the second message should follow the first message, right? So as long as I generated a message or received a message after a previous message, the second message causally follows the first message. Make sense? Okay. Causal multicast at all sites if M1 is less than M2, M should be processed after M1. So I don't know if this is the way I should have phrased it. If M1 is less than M2, then at all sites M2 should be processed after M1. Okay, that's what causal multicast is. Processed. Messages may be received in wrong order, but it should be processed in the right order. Okay. And how to detect and ensure causal broadcast? Okay, that's the question. And okay, so we could send the real-time scalar's timestamp. And what exactly went bad with the real? What was really bad with this real-time timestamp? Okay, so firstly, we are assuming that time is somehow ordering, but each computer may have its own clock. Okay, that's one problem. What other problem?
Also, you can't tell whether there are messages between two times.
You don't know whether there's a pending message or not, which is the problem we ran into in the two-user case.
Yeah, I mean, you could do something weird, like just wait what you think the delay is going to be, and then order them in time and display them. It's not satisfying.
You can try to wait, figure out what the delay might be, but you don't even know whether the guy is ready to go for lunch or not. Yes, maybe at 12 o'clock your stomach is telling you, that a message is arriving. Okay, everybody's stomach probably is telling them that this is lunchtime or beyond lunchtime today since the clock has changed.
What I'm saying is, like, if there's if you know that delay in this network is only going to, worst possible case, this is a big assumption, it's going to be a certain amount of seconds.
Right.
That if you always wait that delay, and then, I'm not saying this is a good solution, but just that it is a solution. If you wait that and then you order on time and display everything you have in that gap.
See, what Jun pointed out is fine. There are many issues arriving here. The one you're thinking of is that somebody sent a message and there was a delay before that message is received. But it was timestamped with the previous message, right? And you're saying, two messages at two different sites. If we know the delays, we can try to figure out which got generated before which. But the first problem is that we don't even know, the clocks may be diverging. Okay? So all this stuff, these calculations makes no sense if the real time is wrong. Okay? And then these delays make sense only when you're anticipating messages. You may not even know the message is arriving. So you don't know whether to wait for the message or not. Okay? Given two messages that have arrived with the right times and you know the delays, yes, you can order them. But when a message arrives, you don't know whether to process it or not. Okay, Nick?
I was going to say, this also doesn't work at relativistic velocities. And so if we want to be forward-thinking, we should come up with something.
No, what, you mean by relativistic velocities?
I mean, if one of these computers is traveling at close to the speed of light.
Don't get me into relativity theory here now. I forgot that stuff a long time ago. Okay. We are assuming that if M2 is caused by M1, then real-time stamp of M2 is greater than real-time stamp of M1, right? We are assuming that. And we can say that process received messages in order of real-time thing, but just because RTS M2 is greater than RTS M1 does not mean that M2 is caused by M1, okay? It goes both ways. And do not know if there's an in-transit previous message, how long to wait, and clocks at different sites may not be synchronized. Okay?
We are still agreeing on a global.
No, I'm saying here's the intuition. And here's why the intuition doesn't work. Because there is firstly no global time. Even if there was a global time, these two conditions would get away. Okay? So some people are talking about going to some satellite and getting the time and figuring out exactly now the network delay issue becomes important. Okay, if you know exactly how how long it takes to bounce a message off a satellite and everybody's going to the same satellite, maybe you can globally order them. Okay, but you would have to know there have to be no routers that are going and changing the delays. But even if you had these clocks synchronized, these two problems get in the way. Okay, two messages may have been sent concurrently, may have no causal order between them, and you might think that they are causally related. Okay, and when you get a message, you don't know whether to wait for it or not. Okay, so this is not working. What might work? And Nick, long time ago, I asked a question. You raised your hand. So.
Oh, I don't.
Okay, but anybody want to?
I think what I was going to say is if like person 1 and person 2 are communicating, and person 3 is observant in this communication.
Okay.
Person 1 and person 2 both have an accurate representation of the order of their messages because they're using their own connection. Like we're doing like sort of pairwise connection things.
Right.
So there ought to be some way they can communicate that to person 3.
So, okay. So what you're saying is PC1 or person 1 and person 2 are communicating. And in this case, these two guys sent messages and this guy was observing the messages. Of course, he generated a message later. And as long as we can order these two order messages between them, somehow that order could be communicated to the other side. And that's a key. That somehow the order of messages, the causality relationship, has to be communicated to other sites. Whether they're observing or not, we just have to do that. And let's just put force method. What if I go and send with each message all the messages I've received so far? Okay? And I put a little global ID there. And a global ID, and what could a global ID of a message be? So I need to be able to give unique IDs to every message. And with each message, I send the history of all the previous messages. So how could I globally order a message among n sites without going to some centralized process to get the ID? How could I give a unique ID at a particular site? And how could I then use that fact to do a global ID?
Can be the ID of the sender plus the counter for that.
It could be the ID of the sender plus some counter. Okay? So this guy goes and says, here's a message done. Its global ID is, I'm site 1, and the next counter number is 1. So its global ID is 1, 1. Okay? And I have received no messages so far. It sends this message here. This guy goes and sends a message saying, I'm site 2. This is my first message. And I have received the first message of site 1. Okay? And when this message arrives here, this particular computer says, oh, you received this message, huh? I haven't. So let me go and buffer you. Like the idea?
I feel like that list will start to get very large.
Will get very large? How large do you think it'll get in practice?
Ancestors. I mean, theoretically it can get in.
Theoretically, it can get very large. Practically, in your assignments, have you ever seen it get very large? Yeah, assignment 1, assignment 2, assignment 3, assignment 4. Think of all of them.
You're talking about like window events?
Yeah, telepointer events. So send all the telepointer events. You know, in telepointer events, you might not care about causality ordering because, it'll eventually, as long as the last message is event is right, it'll have a little jitter, but it won't cause that many problems as this particular case. But still, okay, so this works, but it's very inefficient, especially for telepointers, okay? And you don't want the mouse to be, well, in a telepointer case, what will have to happen for something to go wrong is that one site's telepointing effect is being mimicked or copied by another site, let's say. And then, let's imagine there are 2 telepointers, one for each user, and they become, one telepointer gets ahead of the other one. One guy's following another user, and it appears to be the reverse. So can we somehow make it more efficient? We have to, as Nick pointed out, we have to send some information to this guy about the cause. And here I'm sending the whole information, everything. Could I send something smaller and still get causality? Okay, 2 answers I'm getting, 3, I got many answers. Can I use a global counter? But what would a global counter be? I'll have to go to a process, get the counter of the next message, then send the message.
So when site A send the message done, the global count will be 1. And when site 2 received that message, and he wants to send the message launch, then the global count will increase by 1. So when site 3 received the launch, and the global counter is 2, so he needs to wait to receive the global counter once.
Okay, so what you're saying is, which is interesting, that you start with everybody having a counter of 0. Every time a message is sent, you increment the counter, okay, and send the message. And now if this particular site gets a message that is not the expected message, count message, then it'll wait. Will this work always?
The issue is that how do you synchronize these global counters?
No, what he's saying is messages synchronize the global counters. So they all start at 0. Every time a message is sent, you increment it, okay? And you wait if the next message is not that value, the expected value. So if 2 guys send the message concurrently, we can't tell the difference, right? So it could be the case that there's another site, and this guy sends a message to another site also, and that site goes and sends the number here, and so he's got 1 and 2, and basically if there are 2 guys who are sending the message concurrently, they both incremented the same value. Okay, that's what's wrong. So this counter is not atomically being changed. So whenever you have a global counter, you have to have a synchronized method protecting it. Right? As long as there's a relay of some kind, that there will be a sequential interaction, and no concurrency, and it's a very expected value, then it's okay. But as long as there's some concurrency, you want to detect concurrent messages also. We won't be able to do much with concurrent messages here, but you want to be able to detect them and fail if necessary, and the global counter won't do that.
user 3
Oh.
also?
There's history because you get the global IDs. Okay, what we're doing is we are getting this guy, this site. So your question is, can the same problem occur with the history?
Yeah.
Can it?
How does PC2 know if PC3 had sent?
So let's look at what happened. PC2 sent lunch, right? And it said that 1 was sent before it. This was the cause of this message. And what does PC3 do? It says, I haven't received this message, this particular message. So each message has a unique ID.
Yeah, no, but I'm talking about different. If PC3 and PC1 send at the same time.
Send at the same time. Okay.
And
If-
PC2, how does PC2 decide which comes first?
Okay. So PC1 and PC2 will, if two messages are sent at the same time, PC2 can at least figure out they were sent concurrently. And then it can go and tell the user, hey, something bad happened here. Okay, do you want me to process this message? Do you not want me to process? At least it can detect that fact. With a global counter, I can't even detect that fact. Because it might be 2 because of a different sequence of messages, and it'll just process and say, everything was fine. Right?
How does it matter which message it decides to accept first if PC1 and PC3 send it at the same time?
Okay, so what you're saying is
There's no causality between them.
there's no causality between them, right? So the question is, what do we do when messages come out of order? There are many things we can do. We can try to order them in some funny way, or we can just not process the messages and say, you know, something bad's going to happen, I'm just going to discard that message. But at least I detected that it was concurrent. Okay? And supposing it doesn't matter. Supposing these concurrent messages always commute. What can happen with this global counter is that this particular site might think that a particular message is causal, whereas it is not causal. Okay? Basically, the causal relationship, it cannot detect any longer. Okay? So what we would like to do is detect the causality relationship correctly, and then who knows do what with concurrent messages. But we can't detect that with the global counter because messages may be sent at the same time. Okay? Questions? Okay. And you guys are convinced that the causality relationship, maybe you may not detect the causality relationship correctly with the global counter. So what might happen? This guy sent a message to two different sites, PC2 and PC4, right? And PC4 incremented the value to 2 and sent a message here. And then this guy's message arrives, and he says, "Oh, it's sorry, that other site incremented the value to 1. Did it to 2, right? So this guy sent the message. He increments to 2. Another site increments to 2. Now we have 2 messages coming with the same timestamp, and you cannot distinguish between them. And if you can't distinguish between them, you don't know whether the cause has been received or not. Okay, so that's the overall reason. Okay, so global message ID plus history of IDs of sent received messages. Global ID is unique site ID, not it, plus sequence number. History can get large and compression needed. Okay. So now, what was your answer going to be?
I'm thinking about you can represent the previous site and also the global country and send it with the message.
Okay. So what do you send? What you send?
For PC1, I send 1 and 1, and for PC2, I will send 1.
Sorry. Here I will send what? Here first I will send nothing.
Yes, just nothing.
Okay, the other site will then send?
Send 1 and 1. And because it's received, the last message was received from PC1, and PC2 just received just one message. And I increment the number to then I just send it to PC3.
Right.
It's 1 and 1, and PC3 will send 2 and 2 to PC2 and PC1 because PC3 was received a message from PC2.
So it'll send the immediate, the message that caused it. It'll send that particular, and it'll send 2 and 2, meaning it'll send the highest.
The first 2 is the representative of the previous sender, and the second 2 is the counter.
So PC3 will send 2 and 2 to this guy. Will it send 1 and 1 also? But 1 and 1 caused 2. So it's sending just the preceding cause, not the one before that. What if some other site has got PC2's message but not PC1's message?
That's okay, because no site is going to display PC2's message until after it receives PC1's message.
So
We're kind of like building a local tree from the messages we receive.
So we build a tree, and what you're saying is you just send the previous link, and that's enough. But again, what if again there is concurrency?
So, if same problem, if PC3 and PC1 send at the same time, then PC2, as it can send only one previous, then how will it send like when there are 2 concurrent messages?
So again, concurrency is going to get in the way because you're not sending all the causes. You're sending just the previous message link.
Okay, so what I was considering, and I don't know how this compares to we were just talking about, when you send a message, you send the IDs of every message you've received since the last message you sent. Because assuming that messages are reliably delivered, it seems that the other users will be aware of all the messages you're excluding because you included them in another message you sent out.
So what you're
Now I'm wondering how that deals with if I send 2 messages and they're received out of order.
actually these schemes do assume that messages from a particular site will go in order, but the solution I'm going to show you doesn't make that assumption. We could make, in practice, TCP/IP is going to order messages. Okay, so a message from one site will always be delivered in order to another site. But before we go to the solution, we're trying to save space, right? We know this solution will work when we send the history. We know a global ID doesn't work. We've kind of convinced ourselves that sending the previous message, the counter of the previous, the ID of the last message received can cause problems with concurrency. And I kind of hinted to you what the solution might be because you get information about only one site. Can you get information about all the sites in the message and yet not have the message blow up? And will that, that's easy to convince ourselves will work. So your solution is that send the most recent message from one site that you received. What's the generalization to n sites?
Send the last process message from each site.
Send the last process message from each site that you received. That gives everybody a complete picture of what you received. Okay. And again, with your approach, I might receive 3 messages from 3 different sites and then send a message in response to all 3 sites, right? And if you're asking me to only send one message, only one link for each message, then that information is lost. So not only is concurrency creating problems, but we don't know all the causes of a message, right? I might have received yes, lunch and done, and they said yes, yes. And that information is not being captured by just sending one value. Okay, so a message may not have one cause, but it may have multiple causes. And that's what we're not capturing. Okay? We could do this thing about trying to figure out, what messages, every site has information about, the history of what I have seen, but that's a little more complicated scheme. So what Nick was suggesting was that we keep track of all the messages that I received since the last time I sent a message to a site. Okay, that's a more complicated algorithm, but this is simple, and simpler scheme possible if message not multicast to arbitrary user set. Class actually. We're going to review. So we were looking at causality, and we said that if you really want to do causality directly based on what its definition is, what we could do is send with each message the history of all messages that were received before it was sent. Okay, so initially we go and send this message, and there's no history, and then when this message is sent, we say, okay, so this message's ID is the site ID and the message ID. This message's ID is again the site ID and the message ID, the count, which is the count here, and the history. Okay, and then when this guy sends a message, it sends also similarly its unique ID and the history, and that's enough information to detect causality. Okay? And we said we want a better scheme. So the scheme is you send global message ID plus history of IDs of sent received messages. And the problem we saw was that the history can get large, and we would need compression. Okay, so we saw 2 alternative schemes to compress, and I did a lot of hand waving, or actually waving of the pointer, I guess. These 2 schemes proposed in class carefully to see if that pointer waving was really right. So your scheme was to keep a global ID with each site, right? One number. And every time a message is sent, okay, whenever a site generates a message, it increments the ID and timestamps message with it, right? That was your scheme. So if I go and send message from 2 to 3, and I'm going to send it to other sites too, but this is the one that's reached, I increment my count, and I pass 1 to it. Okay? And similarly, and the problem I mentioned would occur when we have concurrent messages. Okay, so let's go and bring, as long as there was one causal order and there was no concurrency at all, that scheme should work. Okay? And I say should because we're not providing a proof of correctness here. So similarly, this guy sends a message, and it increments its ID and sends it to this guy. Okay? So then the question becomes, what does a site do when it receives a message? And we saw that when it receives a message, it delivers a message if its global ID is the successor of the current global ID. Okay, otherwise it buffers the message to be delivered later. Okay, so in this case, actually, yeah, right. So the received message's global ID is the successor of this ID here. So this message should be delivered, right? Similarly, this message's global ID is a successor of this particular ID, so should be delivered here, right? And then this site should go and increment the count. Each of these, so on delivering a message, a site set its global ID to the message ID. Okay, so this guy sets it to 1, this guy sets it to 1. That was the scheme. Okay? Otherwise, it buffers the message. And what can go wrong here? So far, nothing bad has happened.
There's no way to determine a consensus for the order that A and B should appear for each user.
Okay, so there's the general problem is that we don't know in what order these two guys should be processed, right? And that's a problem. And this algorithm. So what should we do when there is? What should we do when we have concurrent messages? Is a question we briefly looked at last time. Causal broadcast doesn't address that. Okay, causal broadcast says that I should not deliver a message until all of its causes have been delivered. Okay, so there is no global order, that's true. But will this scheme cause our attempt at causal broadcast to fail? Can messages be delivered out of order now that are causally related? Can a message generated by PC3 be delivered before its cause is delivered?
Okay, so we have messages A and B. Then PC3 sends a message to PC4. That's some message C with ID 2. Then PC4 is going to display that message before it receives B. Because it sees, all right, its counter is 1, it's receiving the message with successor, so it goes ahead and displays it.
Excellent. Okay. So PC3 sends C with counter 2. That 2 is a successor of 1, and PC4 merrily goes and increments its counter, and it has delivered C before it delivered B. Okay. So that was your scheme. So if no concurrent messages ever occur, this scheme should work. Okay. Again, I'm saying that causal broadcast, by its very name, does not indicate what should happen with concurrent messages. Okay, and this is something that we look into today. You could deliver it immediately and say, look, concurrent messages must be commuting, no problem. Okay, that'll make our scheme much more complicated, our algorithm much more complicated. Or it could flag an error and say, all bets are off after this. I'm doing quote unquote best effort delivery now. Or it could just say, fatal error, this shouldn't have happened, it has happened, I am suspending any more execution. Okay, so that's something that we are going to leave undefined, and in your extra credit, you can do different things based on, your regular credit. You can throw a fatal error, or you can just throw an error and say, who knows what's going to happen after this. Okay, in extra credit, I'll tell you that, why don't you guys try and make things work, assuming the messages commute. Okay, but causal broadcast should allow detection of concurrent messages as soon as they arrive. Okay, so it should be able to detect that, and we haven't been able to detect that C is concurrent with A. A has been received, C we know was sent, is not ordered after A and C, and so it did not detect the error, and it should not deliver a message before its cause. And that's exactly what happened. And so in that sense, in that respect, this scheme doesn't work. Okay. Questions? Okay. So to solve this problem, we had another solution proposed, which was again more economical in space than the one than the vector timestamp we talked about. And it said that, look, each site keeps account of all the messages it has received from other sites. And in this picture, I'm also showing you that it keeps count of all the messages it has generated. By the way, I'm distinguishing between generating a message and receiving a message from the reading I've done of vector timestamps. they don't distinguish between these two. It's assumed that when you send a message, you receive that message. Okay? So, and everybody else receives the message. And that receipt can happen immediately or it can happen later. If it happens immediately, it's called asynchronous. If it happens later, it's called synchronous. Okay? So I'm just using a different semantics and I'm saying, okay, you generate a message, okay, and send it. You generate and process a message and then send it to others. But in the literature, sending a message implies receiving the message when you're talking of everybody broadcasting messages. Okay? Maybe that's more uniform. So each site keeps a receive count for each site. Okay? And when a site generates a message, it sends the sender and count of the last message it received. Okay, so we assume that, okay, if things are happening causally, we just have to send the last timestamp, not information of the last message, not information about all the messages it has received from all the sites. Okay, so PC2 generates a message B. There is no previous message, so it sends nothing except for the message saying, look, there's no predecessor of this message. And PC1 sends A and again sends no predecessor of the message. Okay? A site delivers a message if the received count for the site is the same as its count for that site. Okay? Otherwise, it buffers the message for later delivery. Okay, so it says, let me look at the cause. If the cause, the most immediate cause, if I have received that most immediate cause, then I will deliver the message, otherwise I won't. Here there is no cause, so it says, cool. And on delivering a message, it changes the count appropriately. Okay, so this message came from 2 to 3, so this particular number should change to 1. And this message came from 1 to 4, so this particular number should change to 1. And now we know, we are keeping the counts correctly. Okay, just as in vector timestamp. Now PC3 sends a message C, and it says, by the way, before C was generated, I received from 2 1 messages. Okay? And PC4 finds this message and says, oh, have I received a message from site 2? No, I haven't. So it buffers it for later delivery. Okay? So the scheme seems to work. We are not sending the whole vector timestamp. We are sending only the most timestamp related to the site that sent the most immediate previous message. Okay, and I again did some pointer waving at that point to say why this wouldn't work. And anybody want to reconstruct a scheme where it wouldn't work, or give the general condition under which it won't work? I'm sending only one number, or one element of the vector timestamp. I'm not sending the whole vector timestamp. And that could be an important efficiency thing. When you have lots and lots of people collaborating, the vector timestamps can get very large. Okay? And so or lots of replicas. I'm assuming collaboration. This stuff got invented in the context of fault-tolerant computing, and having, I guess, fault-tolerant and availability. It's mostly been focused on fault-tolerant computing, where there's lots of replicas of data. Well, it may not be too many in that case, if we're just doing fault-tolerant. If you're doing availability, there may be lots of replicas, okay, that we want to keep consistent. So can we construct a scheme, or can we give a general condition under which sending just one count will not be enough? Multiple causes of a message, and it could be, so that's going to be the reason. And the question is, can these causes be delivered out of order at a site? Right? That was the question that I think Nick mentioned. Won't the causes be delivered can we use the induction proof here that if it's true, if we can do for 1, we can do for 2 and 3 also. Okay. So let's go and look at this scheme here. 4 computers again. Site 2 sends B to 3. Site 1 sends A to 3. Site 1 sends, okay, so the numbers are getting incremented. Okay. Site A sends message to 4 also. The message is being broadcast everywhere. In the previous picture, the reason why certain messages didn't reach other messages is not because they weren't sent to that. The reason why certain messages did not reach certain sites was not because those sites were not going to get those messages. Those sites just hadn't got the messages so far. Okay, so PC2's B message hasn't gotten to everyone so far. It's gotten to PC3. PC1 concurrently, again, we have to assume some kind of concurrency to make this fail. Okay, PC1 sends A to both, sends to everybody, and 3 and 4 both receive it, so they change their counts appropriately. Now, what bad thing can happen? We have 2 causes here. Okay, we have 2 messages going to PC3. So after, and B came first, and then A came. Okay, so we must now send a message from this site to some other site. That has received the most immediate cause, which is this site. Okay, this site has received A, but it has not received B so far. Okay, this guy receives both of these messages, sends to C, and says, you know, I've received one message from site 1. It says, so have I. Okay, and before this cause is received, the message is processed, and it merely changes the number. Okay, so that motivates sending the whole vector.
You can send 2, right?
Sorry?
You can send B, you send for A, you can send for B also, right?
So that was the scheme we came up with. The point is to show an example of why sending only one count is not enough. Okay, why not send the whole vector? Okay. Now it could go and remember what vector it sent previously and send a diff between that vector and the new vector. Okay, I'm sure there's been so much work on this area that to find the paper on it is so hard. Okay. Because when people think of distributed computing, they think of vector timestamps, actually. Okay. So, or they think of timestamps, or logical timestamps, I should say, not vector timestamps. The whole point is that we're not sending real timestamps, we're sending timestamps that show the order in which messages were processed, okay, rather than the times. Okay, that's a basic take-home, and there are many versions of that. And again, if you search for it, it's even hard to figure out who invented, unless you go to Wikipedia and it'll tell you. And hopefully that information is correct. Okay. So I'm just motivating this. And you said you could just send those 2 guys. If send those 2 guys means that it sends a diff between the last timestamp it sent, or the initial timestamp, and the current timestamp. Okay. So in your assignment, just to make sure you don't implement this scheme and the previous scheme, please go and test your system on this, okay, to see that the concurrency is actually caught. Okay, and again, you should do this at the end because things may fail after that. Okay, once you have concurrent messages, who knows what's going to happen? Messages are not ordered. Okay, but at least you caught the concurrency. Okay, and again, when you look at a causality, you know, one of the requirements is that you catch a concurrent input. Okay, questions? A message may have multiple causes, and this scheme sends only the most recent cause. So what do you think took me longer, making the slide or coming up with the flow of interaction? I was being very lazy first. I did this over lunch. I just took a nap. I had a napkin and met Delhi, but I was having lunch and tried to figure out both cases. And that was within an hour. And then it took me a long time to come up with all the animations and get it right. Okay? But I think it's good. You shouldn't do any hand waving when it comes to these precise things, and you should really show all the numbers and so incrementing. Okay. So we're going to assume in this scheme will work only if all messages are broadcast. If we are doing partial multicast, then the scheme is not going to work. That I send to two sites, you send to another two sites, then it's hard to go and use this vector timestamp to order things. Okay. So, and many applications follow this assumption. So we just keep counts of sent received messages rather than the whole history. Okay. And these counts tell us the whole picture because of this assumption that every message is being sent to every other message. So we don't need to look at the whole history. We can just keep the counts, and we know that from these counts with what messages some other site has received before. Okay. So what we're going to do now is rather than keep a number, we're going to use a vector timestamp. A vector because it's got multiple entries. And okay, so this is every message is going to have a vector timestamp. We're going to still keep an ordered buffer. Okay, but this message will be ordered by the vectors rather than by numbers. Okay, and we need to also be able to increment we need an increment operation for these vector timestamps before sending. So before sending a message, I have to increment the message, and after receiving a message, I have to increment we saw that we have to increment a count, and we're going to do the same thing with vector timestamps. We can either increment the count or we can copy the count from the message. Either thing works. Okay, and we also need a successor function. We have to know whether a particular message is a successor of a previous message. Okay, so how would we go and what will be our basis for less than and equal in a vector timestamp? Two vector stamps are equal if. So the vector timestamp has a number for each user, which says these are the number of messages I've received from that user. Plus, it has a number for itself also, because we're sending a whole vector. What would the number be for itself? If I've generated a message, and then I receive a message after that, and I send a message after, I generated a message, then I received a message, and then I sent some response. That message was caused by how many messages? Preceding message plus my message. So it's got to keep account for itself. What will it do? So let's look. Vector timestamp is x1 to xn at site sj. The value of xi is what? If I is not equal to j, the value of xi is? At site sj, we keep a site vector timestamp, right? So xi, where I is not equal to j, is
the number of messages that I received from site 1.
site I. Okay, number of messages received from site I. And xj is what?
The number that I already sent.
That I've sent. Okay, so think of that pair that we kept at each site, local number and remote number. That was really a vector of 2 elements. We've generalized that to n elements. Okay, by having other than having 2 different variables, now I have n variables, including my own site. And remember in causality, I said I took my own messages also in consideration. Okay, Nick, you had something?
Yeah.
Okay. So site Sj has broadcast Xj. This should be Xj, not I. Okay. Site Sj has broadcast Xj messages to all other sites, And for all I between 1 and n, where I is not equal to j, site sj has received xi messages from site I. Okay? And this should be xj. And these two are equal if two vectors times are equal if
All of their entries are equal.
okay. Vector timestamp 1 is less than vector timestamp 2 if
One of them is less than.
one of the components is less than and the other components are the same. So one component is less than and the other components are all the same.
Maybe same.
If anything's less than, that's all you need for it to be less than.
Okay, so let's get it right. So V1 is less than V2 if how many components are less than? Exactly one component is less than?
At least one.
One or more.
One or more is less than and the other components are?
Equal or less.
Yeah, less than.
Cannot make it.
Okay. So I can say that there is at least one component that is less than, and the other components can be less than or equal to. Right? So we now don't have a single number. I can be less than many other timestamps. Okay? Because those timestamps could be generated concurrently. So we have okay, so and we'll see that here. So successor. So vector timestamps do not create total order. Right? You can have one component less than, another component greater than another timestamp. In which case these two timestamps were, these two messages were sent concurrently, which is something we can detect now. Okay? So possible that AI is less than BI and AJ is greater than BJ for some IJ, and that implies we have concurrent messages, and typically they denote that as V1 is concurrent with V2. Okay.
I mean, it implies that they're inconsistent.
Inconsistent or they're concurrent, right?
Right.
I moved the line, you moved the square. Okay?
Or that there's an error in your code. That there's something happened to one of the clients.
Okay, so concurrency can occur for various reasons. It could be because two operations that commuted was sent concurrently. Okay? It could be that always something bad can happen because of an error. Okay. So causal broadcast does not impose order on concurrent messages. Okay, there's something called atomic broadcast, which imposes order on concurrent messages. And this is a problem we're going to solve when we look at operation transformation, okay, to some limited extent, or for a particular application. So that's very important. We want to be able to detect concurrency, but we really don't know what to do with concurrency. Okay, we don't want to get confused about what is causal, what is not causal. Okay, but we don't know what to do with concurrent messages right now. And in your project, you guys are free to do whatever you feel like. You can just, when a concurrent message arrives, you can just not process it, or you can just process it and say, must be commuting. Yeah, that's what I do. In my implementation, I just process it and hope for the best. Okay, or you can just assume that you will not even give it a non-causal, a concurrent example in your demo. Okay, so we have now less than equal to a sorting buffer. What about increment and successor? So what is the increment function going to look like now? With a single number, we just went and incremented that number. With a vector timestamp, what does increment mean? So when we are sending a message, what are we incrementing in the vector timestamp? So I go and, I have a vector, some vector here, which is my current time. I send a message, I'm site j. What am I going to do to the vector timestamp? I have to increment it. What does that really mean? There's a vector of elements. Increment the jth component. Right? So increment now takes as an argument which site you're incrementing with relative to. And when I receive a message from some site I increment xi. Okay? And successor function, when I have a number, we know what, if the number is 5, we know its successor is 4. In a vector, what is the successor of a vector? How many successors can a vector have? There can be n successors. So we so things are becoming more complicated, different, but so you are a successor of a previous message as long as exactly one component is more than the previous one, right? So V1 is a successor of V2 if there exists some I such that AI is equal to 1 plus BI, right? And all the components AI is equal to all of the components AJ is equal to BJ. Right? So you can be a successor of many different vectors. Okay? And inc takes that vector timestamp, takes a site and just increments the count for that site, okay? Which is what we saw last time. Okay? Questions? So message has multiple successors and inc with respect to a particular site. So each pair, this is our algorithm now for the two-person case. Let us extend it to the multicast case. So each pair of communicating computers keeps a count of how many messages it has sent to the other party and next expected remote number for each party. And that gets replaced by what now? A vector timestamp. Okay. Attach and increment local count. Now what do? We saw that. Increment II and attach vector timestamp. We just saw that previously. Each site keeps ordered buffer for other party. How many buffers do you keep here? Still one. Okay, that's the whole idea of creating an order. When a message received, put message in ordered buffer. And everything else can just stay. We've got successor function. We've got this. It was remote number is message number. Now we say remote TSI is message TSI. Look, sorry, the ith component of my timestamp is the ith component of the received message timestamp to record the fact that I received the message. And that will also be an increment because messages will arrive in order. Will be processed in order at least. Even if they don't arrive in order, they'll be processed in order. Okay, go to one. So the algorithm, the reason I took this two-user case, which is not traditional, I don't know if anybody else has done that, is to make this case simpler to understand. Okay, so I hope this is correct because this I did from first principles, but I believe it is. Okay. Again, we're not going to go through a detailed proof here. So let's go and see how this works. I have a message done. I send message, that means I increment II and attach vector timestamps. So I go and increment my site 1, attach 100. Okay. This message arrives here. What is the site going to do with this message? It puts it in ordered buffer. Okay, that was the algorithm. And if buffer is empty, or it's not the timestamp is not the successor, return, but it is the successor. Remove message from buffer, process it. Local TSI becomes message TSI, right? So this thing became 1. Now he sends a message lunch, and the timestamp of this particular message will be 1, 10. Okay, so it went and also incremented its count, 110, and this message now is put in ordered buffer. And is this the successor of the previous timestamp, 00? Go back, and then this message arrives, done. Put it in ordered buffer, and it gets put ahead of the message. Remove, is the message at the head the successor? Yes. Remove message, done. And now we have to go and increment the timestamp, 100. Now we go to 1, remove the message, lunch, local timestamp, increment, and it works out. Okay? So when you implement causality, you have to do some work now. Okay? It doesn't seem very complicated, and it isn't, as long as you understand the theory well. Okay? But you have to implement vector timestamps, you have to implement the buffer, you have to change message sends and receives. To do that, to timestamp and untimestamp a message,